Hi guys, my name is Tensor. Welcome to my first video on Rust Async-Await. Today we're going to be building a practical example. This way, when we fall back into the fundamentals of Async-Await, we'll have something to refer to. In this video we'll be building a web crawler, and I've brought in 4 different libraries that we'll need to do this. I've brought in a library called Async-Std, and this is quite literally the standard Rust library written with Async-Await in mind. Then I've brought in Surf, which is an HTTP client. Again, it utilizes Async-Await. I've also brought in HTML5ever, which is a module from the Servo project, which will allow us to easily parse the HTML that we get. And then I've also brought in a library called URL, which will allow us to determine whether or not the URLs that we're getting from the web pages that we're pinging to are valid. Now, the first thing that we want to do with this application is write the internal logic so that we can parse the HTML and identify the proper tags that we need to get the URLs that are on the page. We'll be bringing in a lot of stuff from HTML5ever, specifically the tokenizer. We'll bring in the buffer queue, we'll bring in the tag type, we'll bring in the tag kind enum, we'll bring in tag token, we'll bring in token, token sync, token sync result, tokenizer, and tokenizer ops. Also, we're going to need standard borrow, and we're also going to need some items from the URL library, namely the parse error and the URL type. As you can imagine, as we're crawling over a web page, we're going to have a lot of links. So we want to create a struct that will allow us to keep all those links inside of a nice vector. We can create a struct here called linkQ, and this will be the struct that we'll use to contain all of the links that we're crawling on top of. For the linkQ struct, we want to derive default so that we can default the values in the struct. If we initialize this struct with a default value, that'll mean that the vector for the links part of the struct will just be a vector new. Because we want to be able to see all of the links inside of the queue, we'll derive the debug trait on top of it. For us to be able to use the tokenizer from HTML5ever, we want to take the token sync trait and implement it on our linkQ struct. And because our linkQ is going to be mutable, we'll do it like this. Now, the token sync trait has a few things attached to it. Namely, it has a type, which will be the handle of this sync. Then we've got this process token function, which is essentially the main function that we want to implement. But there is also an end function, and then this other function down here. These two functions we can mainly ignore, but these two pieces we want to implement. We'll make the handle type into a union type, and then we'll implement the process token function. Process token needs to take in a reference to mutable self, so mutable link q, and then it will take in the token type and then the line number, and then it will output a token sync result. And because we specified that the handle will be a union type, we'll put that handle inside of this result. The token sync result type is just an enum type, and we can use this enum type to specify what we want our function to do after it passes over one of our tokens. So once we find a link, we want our function to continue to parse the rest of the HTML to find all of the rest of the links. So we can use the token sync result continue type as our return type from our process function. But before we return this token sync result of continue type, we want to match on the token itself so that we can make sure that we're getting A tags from the HTML. The token type that we're matching on has a bunch of different values that it can be because it's an enum. The one that we're worried about is just the tag token. So the tag token just means that it's a normal HTML tag, and that's what we're looking for. So we're looking for an HTML tag token of A type. To make our pattern match exhaustive, we can set it up so that we look for the tag type specifically, and then we just have a catch-all which catches the rest and just throws them out. Now remember, we're parsing through HTML, and an HTML tag, an A tag, would look something like this. Each tag inside of an HTML document has two pieces to it. It has an opening tag and a closing tag. And inside of our code, the tag kind can either be a start tag, which is this opening piece, or it can be an end tag, which is the closing piece. We're specifically looking for the links inside of A tags, so we want to look inside of the start tag. So what we can do is pattern match on the tag type, and we can say specifically that we want to look at tags where the kind of the tag is a start tag. And once we've determined that the tag is a start tag, we can go ahead and just run an if check to see if the tag name is A. Opening tags can have multiple attributes inside of them, so we want to take the tag that we've identified, grab the attributes, and then iterate through all of them. And we can do this just simply by turning the attributes into an iterator using a for loop, and then we can check to see if the attribute's local name is just href. After all of these checks, we know that we're looking at the URL string. So we can go ahead and just grab the URL string by calling attribute value borrow. This will allow us to get the value of the URL, and then of course we want to borrow it so that we can then push it into our links vector. Now the value that we're getting from the attribute will come in as a slice of U8 numbers, because it's being read in as bytes. So we want to convert those bytes into a string when we push it into our links queue. Take these in as a reference to U8, and then call string from UTF lossy on our URL string, and then convert it into an owned string as we push it into our links vector. And that does it for this implementation block. Now let's go ahead and create a function called getLinks, and this will take in a URL and a page, and then it will pass back a vector of URLs. So first we want to make sure that the URL is just the domain URL, and we can do this by taking the URL that we pass into the function and cloning it into a mutable variable called domain URL. We have this link that's pointing towards example.com, and it's got other stuff attached to it. So first we've got this query string, and we want to remove it completely. We do that using this set query call, and then we've got the set path part, which is the API example part, and we remove that by calling this. Now we can go ahead and instantiate one of our link queues by using the default method, which we derived earlier. And all this will do is it will just zero out the links vector inside of our link queue. And with our link queue, we can now go ahead and create the HTML tokenizer. We just pass the link queue into tokenizer new as a mutable reference. For the tokenizer options, we can just pass in tokenizer ops default. Let's now create a buffer queue. The buffer queue will allow us to essentially go through our page string one item at a time. It's essentially what's responsible for reading through the characters in our HTML page. The tokenizer, on the other hand, is what's responsible for identifying the tokens in the HTML document. So now let's just take our page string and push it into the buffer queue, and we can use push back, which will add it to the front of our buffer queue. And now we can just take that buffer and feed it into our tokenizer. Once we've done this, we can take all of the links which will be fed into our link queue, iterate through them, and then map on top of them to check to see what kind of URLs we have. So we call URLParse on each of the links inside of our links vector, and then this will allow us to determine whether or not we have a valid URL. There's one error case that we want to specifically look for, and that's for if we find a URL that is a relative URL. That is to say that it doesn't have the domain attached to it. On web pages, it's not uncommon to just put in the relative URL rather than the absolute URL if you want to go from page to page inside of your domain. And so we want to deal with this case, and we don't just want to throw out all of the links that are directly connected to whatever domain we're searching on. What we can do is just take those relative URLs and attach them to the domain URL and then pass them back as a new absolute URL. Then if we get any other kind of error, we can just panic and say that we have a malformed link, and then we can print out that link. If we have a normal URL, then we'll get back OK and the URL, and we can just pass that back. To finish this off, we want to collect all of these URLs into a vector, and so we can just call the collect method on our map function here. Okay, so this should complete the logic piece of our URL crawler. If we were to feed an HTML document into this function, it would properly scan over the HTML and find all of the links that were associated with it. But of course, we want to be able to just call to a server using a URL and then have that server feed us the HTML, and then we can continue to call to each of the links. So we need to create a way for us to do this. So to accomplish this, we need to make two more imports. We need to import a sync standard task, and we need to import the Surf client. Now let's go ahead and create some helper types. So we'll create a type called crawl result, which will be a result type, which we get back from our functions. And all this really is a result type that either has a union type on the OK side, or it has an error which has a box pointer and a dynamic error that implements send, sync, and static. Now the send trait allows us to send this error across boundaries. This essentially means that we can just send it across threads. The sync trait allows us to share references across threads. And then the static lifetime is necessary so that this will be able to be returned from an asynchronous function. Next, we have a box future type that we want to implement. And our box future type will be surrounded by a standard library pin, and the pin is essentially just a pinned pointer. That's all you really need to know for now. Inside of this pinned pointer we'll have another box, and inside of the box we'll have an implementation of a standard future where the output is a crawl result, which is that other type that we just created, and the future also implements the send trait. Now both the error type and the future type are trait types, and with this dyn keyword, which you guys may not have seen before, we're essentially just saying that inside of both of these boxes we want to return a type that implements the trait. In the case of our crawl result, we want to return an error that implements the error trait, the send trait, the sync trait, and then the static lifetime, which we can also apply as a trait. And then in the case of our future here, we want to make sure that we're returning something that implements the future trait where the output is equal to our crawl result, and it also implements the send trait. If we take a look at the future trait here, you can see that it's actually composed of only two things. You have an output type, and the output type is the result from the future completing. So it's the value that you want to return from completing the asynchronous block of code. Then the only other thing inside of the future API is this poll function, and we'll get to that in a future video. You just need to know that the poll function essentially is a means for us to check to see whether or not the future is ready to return its value or not. Alright, so now that we've implemented these two types, we can go ahead and create a function called crawl. And this will be an asynchronous function, so we can preface the function with the asynchronous keyword. And what this does is it makes it so that this function will return a future type. So even though we've specified that we want to return the crawl result, we're actually returning a future that's wrapped around the crawl result by specifying that this function is asynchronous. The crawl function takes in a vector of URL, which will be our pages. It takes in the current depth, which will be a U8 value, and then it takes in the max depth, which will also be a U8 value. These depths determine how many pages from the original page that we called do we want to continue to crawl. Alright, so at the top of this function, we just want to print out the current depth and the max depth. And then we want to check to see if our current depth is greater than our max depth. Because if it is, then we want to stop crawling. So we'll just print out max depth reached, and then we'll return OK with a union type inside of it. Now essentially what we're going to do is spawn multiple different tasks for each of the URLs that we get, and each of these tasks will spin up what's called a green thread. So they'll run asynchronous to one another on these lightweight green threads, and that will make it so that we can quickly go through each of the pages that we receive. So we can go ahead and create a vector for all of our tasks, and then we can just print out that we're crawling over all of these pages, and we'll just print out all the pages that we're crawling. Now for each URL inside of our pages vector, we want to spawn a specific task, that is spawn one of these green threads. So we can call task spawn, and this is similar to calling threads spawn, except in our case here we're just passing in an asynchronous block. Though of course we're also using the move keyword, which means that we're moving all of the outside variables into this context. For each of our tasks, we'll go ahead and we'll print out that we're getting that URL. Then we'll go and use the surf library to call a get method on that URL. The get function in the surf library will return a future, so we want to await on the get method so that we actually get the future back before we proceed. Then after we've gotten the result back from calling surf get, we'll take that result and get the body string, which again will give us back a future, which we want to await on. We'll wait until we get that entire body string before we move forward and call our getLinks function on both the URL and the body string. We can print out that we're following all of the links that were inside of the body string that we passed to our getLinks function. And after we've done all this, we can take the task that we created and then push it into our tasks vector. Now it's important to keep in mind that even though we're generating tasks here, we haven't actually tried to execute them yet. We're just putting them inside of our tasks vector. To execute them, we need to take them out of the tasks vector and then call await on them. So essentially what we're doing is just going through each of the URLs, getting them from our pages, and then spawning tasks for each URL so that we can continue to follow them. To continue to follow them, we want to recursively call our crawl function after we get all of the links on each of the links. If we just called crawl like this recursively, it would be inefficient. So what we want to do is set up another function that puts our crawl function inside of a box pointer. We'll create a wrapper function called BoxCrawl, which takes in the pages, the current depth and the max depth, and it itself returns our box future type. In the function, we just create a new box pin pointer and we put our crawl function call inside of it. And now we can come down into our crawl function and pass a call to BoxCrawl, pass in the links, then take our current depth and add 1 to it, and then also pass in the max depth. And of course, because this returns a future, we need to await on it as well. And now we're finished with our crawler logic. So all of this will work. Alright, so now let's finish up our application by tying it to our main function. So in here I'm calling BoxCrawl, and I'm creating a vector, and I'm putting in the rustlang.org website. Then I'm putting in a current depth of 1 and a max depth of 2. Now if we go ahead and run this application, you can see absolutely nothing happens. And there's a big reason for this. Because of the way futures are implemented in Rust, if you don't await on a future, nothing will happen. In this case, our BoxCrawl function returns a future, but we never awaited on it. If, however, we add await, you can see that we get this error here that says await is only allowed inside of asynchronous functions and blocks. And because our main function is not asynchronous, we can't call await on our BoxCrawl function in here. What we can do is use the standard async library that we brought in and use the task module and a function called blockOn. The task blockOn function allows us to block the main thread, that is the main thread of execution that the main function is running on, until everything inside of the asynchronous block here resolves. In our case, we're waiting for the BoxCrawl function to return its future. And of course, we put this inside of an async block so that it is properly adhering to the idea that we can only await on something inside of an async block. So now you can see that if we go and run it, it goes through all of the different links and it follows them as we would expect with a web crawler. And actually, considering the amount of links that this crawler had to crawl through, this thing actually went pretty quickly. You can see there are quite a lot in here. And because we're using tasks, we can delegate each of the links to its own specific task. Now, if you really want to see the performance of this thing, you can go ahead and specify an even further depth. So for instance, here I specified depth 4, and then I manually quit it. But you can see that it's getting all of these different links and then following them afterwards. If I had let it continue to run, it would have followed all of these links with independent tasks. Alright guys, well I hope you enjoyed this video. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like. If you want to support the channel, then I recommend going to check out my Patreon. And if you want to see more videos like this, then go ahead and click that notification bell. Have a good night.